1, 2, 2, 2. Okay, let's test. So is it one test case with two numbers 2 and 2, or is it four numbers 1, 2, 2, 2? I guess this. Okay, it's yes. Looks correct to me, because we need to make 0 exchanges. Okay. Okay, so basically I can just ignore this part of the problem and just read it from here. But maybe it's nice, I don't know. Danik urgently needs a rock and lever. The easiest way to get these things is to ask Hermit Lizard for them. And Hermit Lizard agreed to give Danik the lever, but to get a stone, Danik needs to solve the following task. Okay, sure. Problem setters usually come up with those stories. And I think it's up to them. I don't mind them too much, but sometimes when you figure out that the first 3 paragraphs are just useless, it might be annoying. Okay, a positive integer n, an array A, and the number of pairs ij such that I is less than j and is greater or equal to XOR. Okay. ICPC problems do have a lot of stories, but the thing is, I think that in ICPC problems, the story is usually connected to the problem. It's not just some random stuff. Like here, this story has nothing to do with the problem. So I think that's the difference. Yeah, using Midnight Commander like a pro, kind of. Okay, so what does this condition mean? AI and AJ greater than or equal to AI XOR AJ. So let's see. Let's start from just number of one bit, of a single bit. So 0 and 0 is equal to 0, and it is equal to 0, which is equal to 0 XOR 0. 0 and 1 is equal to 0, and it's less than 1, which is 0 XOR 1. Okay, same goes for 1 and 0, and for 1 and 1 we have 1, which is greater than 0, which is 1 and 1. Lizard is a good clue, is it? I don't know. Yeah, it is my birthday tomorrow, but not today. So we can see that if both bits are zeros, then we have 0, so it's equal. And in other cases, it is not equal. So if we have at least one 1 in the numbers, then we always have a non-equality. And when we do bitwise operations, so we have some numbers like this, one number is this, and one number is this. We can have, let's say this is A, and this is B. We can have A and B equal to 0, 0, 1, 1, 0, and we can have A XOR B equal to 1, 0, 1, 0, 1, 0, 0, 0, 1, right? And when we want to compare these two numbers, we can just compare them in the first position where they differ. And here the first position is already the first bit. So we can see that in the end we have 0, and in XOR we have 1. And another case to consider is if A and B have the same highest bit. You can see that in A and B we have 1 here, and in A XOR B we have 0 here. So the final condition actually is that A and B is greater than or equal to A XOR B if and only if A's and B's highest bits match, right? That's the condition. Just because only the highest bit matters. If it's different, then in the position of the highest bit of the bigger number, we'll have a bad inequality. And if the highest bits match, then AND has 1 in that position, XOR has 0 in that position, so we have the required inequality. Okay, so now the problem is how to count the pairs. And we can just see that a pair is good if their highest bits match, so we can just classify the numbers on their highest bits. And count the number of pairs inside each of the classes. Okay, so let's say we have some kind of array of counts. We have 32 bits, so we can just count like this. And to, like, the best way, like the shortest way to do this would be to just count leading zeros in the number. So it would be built in count leading zeros in AI. This is GNU, I guess, C++ specific function, which counts the number of leading zeros in AI. So basically I can do it like this. And I have classified the numbers now. The number of pairs can be large, so we have to use long here. And here we also have to use long in multiplication, not to get overflow. And again, the number of pairs is this. The number of pairs in the same class. So let's check. 1, 3, 2, 0, 0. Okay. If the stream is error 2000, I guess Sometimes reload helps. All right. And you don't have to use this function. So another way to do it would be find the highest power of 2, which is not greater than the number. We can do it like this as well. It's probably not much slower. So we are counting pairs for any possible bit which might be the matching highest bit position. Yeah, something like that. So we classify all the numbers on their highest bit. For each highest bit, we count the number of numbers with this highest bit. And then for each highest bit, we just add the number of pairs of numbers with the same highest bit. Built-in count leading zeros is, well, formally it's not constant time. It's log of machine word size. So in our case, it's int, so like the machine word size. I mean, log of the size of the integer we ask for. So it's 32, so I think it should be like 5 simple operations. I mean, so formally, from asymptotics point of view, it would not be constant time if we include machine word size in the asymptotics. It uses a complicated bitwise operation. Just one of them? I don't think it uses one bitwise operation. I think it uses like 5 of them. Pretty sure. 62, all right. How's system testing going? 62, all right. Going well. Let's go for C1. Maybe let's go for C2, actually. Well, whatever, let's read C1 first. I would go for C2 most probably if I was just doing the contest live, but doesn't matter here. Oh, we have no swap operations, okay. And Pikachu. And they have strengths. We can choose any non-empty subsequence. Okay, the strength is some alternating sum of elements of the subsequence. And sometimes we swap them and we want to find the maximum strength of the army in the beginning and after each iteration. Okay. Okay. Okay, so the first question is, how do we find the answer to just one query? I mean, just without queries. How do you find the best total? We can definitely use DP. We can definitely use DP. Even though I guess that you can actually use DP with segment 3 for C2. But okay, let's just start with C1 just because I can. Because I think that, no, I don't know. I guess segment 3 is still fine. It should not be too hard. But maybe there's easier way. So we are solving C1, so we just are solving for no queries. And DP should be easy. Why are the values at most n? I'm not sure, but okay. You have to choose non-empty subsequence, all right? And it's a minus a plus a and so on, okay. So I think that we just want to find the maximum and the minimum possible subsequence. Basically, we can do it like, we can do it DP. We don't actually need arrays here. We can just use variables, but we can also do it with arrays. So mxi is max strength of a team chosen from AI plus 1, and so on, and n minus 1. And mn is mean. The same conditions, but maximum and minimum. It's not copy paste. Obviously, the problem asks us to find the maximum. So if we can calculate such values, then we can just output a max of 0 here. But why do we find the minimum? And the reason is easy, because if we want to take some element to the sequence, then we can see that the signs will start to alternate from the second element. So basically, we can rewrite this condition. So we have, we want to maximize AB1 minus AB2 plus AB3 minus AB4 plus and so on, which is the same as maximize AB1 minus, and then we put a bracket here. And we can see that if we put everything else beside the first element into brackets, then this part will be the same definition of the strengths, but it is negated. And if we want to maximize it, then we want to maximize the whole expression, then we want to minimize the value in the brackets. So we just say that maximum of I is equal to maximum of, we either ignore the element I, then we just go to a max I plus 1, we just don't use I. Or if we use I, then you have AI, which is AB1 in this case, minus the minimum on the suffix. And for MNI, we have the same conditions, but minimum and maximum reversed. All right, so let's check C1. 3 to 9. Okay, looks good. So it's quite easy. Okay, people said segment 3 was timing out for C2. subsequence is a permutation? Yeah, it actually is. These numbers are all distinct, but then you write that it's a permutation here. Okay, so people are writing that C2 has a much simpler solution than DP plus segment tree. Okay, so DP plus segment tree is obviously what I would go for. By the way, let's mark the problems with yellow maybe. Just a moment. Since we can't test them yet. No, this yellow is not great. Okay, this is orange, but whatever. Yeah, it is a permutation because here we can see that they are, so it's distinct at most n. Okay. C1 can be done without DP. I guess if C2 can be done without DP, then C1 should also be doable without DP. At least without DP plus segment tree. Okay, maybe let's think about C2 in this case. So the DP plus segment tree is kind of the obvious solution, but let's see if we can do better. Well, not like obvious, but kind of straightforward if you know the technique. Okay, how can we actually use the condition that this is a permutation? I don't actually see a good way to check it, to use it. How's system test doing? 73. All right. Can we somehow figure out this structure? Like, I mean, do these numbers have any structure? So we can see that mx and mn are not non-increasing and non-decreasing. So every next value is one of those. I guess that should be actually, yeah, I think that should be symmetric, right? So is it true that mx is equal to mn minus mn for any position? Well, obviously not, because no, for one element it's its value and 0, right? Yeah, because there is some difference here, right? Yeah, okay. Yeah, C2 height permutation. I mean, C1 had permutation. So if you notice that C1 has permutation, then there's no reason for C2 not to have permutation. Okay. mxi, maximum of mxi plus 1, ai. I don't see an easy solution yet. And I don't really see how to use the permutation property. Let's output some debug stuff. Maybe we can figure out when we look at the numbers. Yeah, so after every number, one of the values changes, and the other one stays the same. Is it obviously true? Probably not. Maybe both can stay the same, but probably not both can change. Seven minus 4. Interesting. I mean, well, from looking at these values, I feel like the answer is just the sum of differences in positions where the sequence is decreasing. I'm not sure if there is an easy explanation to that. So I feel like the solution is just something like that. No. One, 1, and 7. No, current minus next is what I wanted to write. Yeah, either consider the first element, or here I consider the last element here. So it's 3 to 9. So it's correct for the sample. And then if this solution is correct, then it's actually easy and much easier to change it into a working solution for C2, just because this, if this solution is correct, then it's actually easy and much easier to change it into a working solution for C2, just because this total doesn't change much. When we just swap two elements, we can just consider four positions, the swapped positions and the previous positions to them, and just see how the difference changes. But okay, so let's see. Oops. Let's see. If we assume that this solution is correct, then okay, so let's have a function like this. I think it's pretty useful, which will return the value at position I. So what is the best way to do it? We can have equal positions swapped, but why? Okay. But for some reason we have L not greater than R. Okay. Okay. And let's also return 0 here, just to be sure. And I think it would be easier. So we subtract the value from position x minus 1 from position x, and we can also subtract the value from position y minus 1 and y. Then we swap ax and y, ay, and we add all these values back. And there is a small bug in this code. Try generating a precompiled header for bits std++. No, maybe I should actually consider it. Is it an easy thing to do? If you have any tips, you're welcome, because I would definitely appreciate that. Speed up GCC compile time. Okay. Yeah, I haven't seen this blog. Thank you. I will definitely take a look. Is it suitable for Windows? Yeah, I guess there's nothing specific to Linux here. Should be fine. The bug here is that if x is not equal to y minus 1, then we have to do this. Otherwise, we subtract it twice, the same position. So you just copy to your local directory. Okay, I'll check it. Thank you. So yeah, so x minus 1, x, y minus 1, and y are the four positions that change. But if x and y are the neighboring positions, then we have to not to subtract and add it twice. So let's see if we can pass the sample test case. 3, 4, 2, 2, 2, 2, 2, 2, 9, 10, 10, 10, 9, 11. Looks correct. Okay, so I'm ready to submit C2 now. And I have not written the segment 3 solution, which a lot of people would like to see, right? have to not to subtract and add it. This case 2, 2, 2. Okay, not written the segment 3 solution, which a lot of people would like to see, right? Maybe not a lot, but whatever. How do I explain this solution easily? How do I understand it, maybe? Because this is what I kind of figured out from the formulas, from the output values. Like literally, if you take a look at these values, I mean, that's just how formally I understood what happens here, right? So we have some max and I plus 1 and mn, I plus 1, max and min, whatever. And we have these formulas. And basically, we have to consider two cases. Let's say AI is less than mx I plus 1 plus mn I plus 1. Okay, then what do we have? We have that AI minus mni plus 1 is less than mxi plus 1. Okay, so assume that this is true. This is less than mxi plus 1, so mxi is equal to maxi plus 1. But at the same time, we have this condition, but here we have minimum. So mni is actually equal to ai minus mxi plus 1. So we can see that if this condition is true, then this is how the values change. And then there is another case. The other case is greater than or equal, let's say, because equal is actually is impossible here, but never mind. Assume that it can be equal. So we have this condition and the other condition. If we just move max I plus 1 to the left or min I plus 1 to the left, so we have max I equal to ai minus min I plus 1, and min I is equal to min I plus 1, right? That's what happens here. So we have two cases, and in one case we have these formulas actually, which are equivalent to the formulas above. I just opened up the maximum and minimum, and these are the formulas if ai is greater than or equal to the sum. And another thing to note that in both cases we have max I plus min I equal to ai, just because in both cases it is true, right? In this case it's true, and in this case it's also true. And so it means that here, when we were assuming stuff, we were comparing it to ai plus 1, and here we were also comparing it to ai plus 1. And finally, we can see how the answer changes, how the max value changes. So in this case, it doesn't change, and in this case, it increases by how much? Basically, well, it increases by ai plus minus ai plus 1, but if you just write down the stuff, I guess it should be easy to see. Is it? Yeah, it should be easy. So that's what we can see. So the maximum of 0 is the total of all these values. Okay. And so that's how we get to this solution. I don't know if there's any reasonable explanation, because my explanation is just working through the formulas and just looking at them from different perspective, like trying to figure out how to simplify the formulas here. Okay, that's it for problem C. So hopefully the tutorial contains some reasonable explanation. I'll take a short 2-minute break, and then I'll be back with problem D. Codeforces Problems, there was warning not to use lon instead of use int64. I think it was not about lon, it was about print f format specifier. Int lon and lon are inconsistent on different platforms. Yeah, that could be true, because, but for now I think it's quite the same on, at least on competitive programming platforms. But yeah, it's not like super specified. So int64 is definitely 64 bytes, but who knows what lon can mean, right? And there was also a question, how many problems as a beginner should solve on daily basis? I guess as many as possible, and as many as you enjoy. That's also a very important point. Okay. We have our old friend 998244353. We have n lamps. I mean, yeah, I can also read this. Ori and Sign have overcome many difficult challenges. They finally lit the shrouded lantern and found Gumon's seal, the key to the forlorn ruins. When they tried to open the door to the ruins, nothing happened. Ori was very surprised, but Sign gave the explanation quickly. Clever Gumon decided to make an additional defense for the door. I wonder how many times I mispronounced some names in this text. Okay, so we have n lamps. We know the time of turning on and off for the ice lamp. And to open the door, we have to choose k lamps in such a way that there will be a moment of time they will all be turned on. And we have to find a number of ways to pick such k lamps. So I feel like this problem appeared before, but whatever. Maybe I have just seen too many problems, but I think it doesn't matter. So we want to find the number of subs. So we have n line segments basically, and we want to find the number of subsets of k, exactly k segments, which have a which have at least one point in their intersection, right? So from 3 segments, 1, 1, 2, 2, 3, 3, choose one of them, it's 3 ways. Choose 2, 0 ways, because no 2 of them intersect. Choose 3 if all are 1, 3, 2, 3, 3, 3, it's 1 because choose all of them, right? Yeah, we have explanation here as well. So here we have 1, 2, 1, 3, 2, 3, 2, 4, 3, 4, 3, 5, 4, 5. All right. So the problem is pretty easy. Maybe it's even easier than C2. And from the number of accepted, yeah, D is actually easier than C2. Fair enough. So the solution goes like this. We have n segments. Your exams are starting from tomorrow. Good luck. Hope you pass them. So the solution is, let's sort all segments in decreasing Okay, in increasing order of L. Okay. The way I usually do it is instead of reordering the pairs LR, I just create an array which corresponds to the order of segments. So I want to fill the array with consecutive numbers, and then, okay, let's do this. And then I want to sort them, let's say in non-decreasing order of L. And then suppose we pick segment, so suppose that we now have them all non-decreasing. Suppose we pick segments, segment 1, segment 2, segment K. So what condition do we have? We want all these segments to be intersecting in at least one point. What does it mean? Okay, so we want segments S1, S2, Sk to intersect in at least one point. So, which is equivalent to the maximum of their left borders should be not greater than the minimum of their right borders, right? That's what we have. That's the condition. What does it mean? It means that this segment from this point to this point is the actual intersection. If we have greater here, then we have empty intersection. Okay, and suppose that we have segments with indices in increasing order, then actually maximum of their L's is already known. It's just LSK. So this is equivalent to this, just because we know that the maximum of left borders is the last one. But we don't know anything about the right borders. So what we do now is let's loop over and let's fix the last segment we take. And we want to know the number of segments which are suitable for this condition. So this is actually equivalent to LSK not greater than RS1, and LSK is not greater than RS2, and so on. And this is obviously true, but the rest of the conditions are meaningful. We can write it here as well. We can write just k-1 here. We need k-1 conditions. Let's go through segments in the order. And the question is how many segments satisfy this condition, that their right border is not less than our current left border. So let's just have a multiset of all right borders. So it will be called Rs. And we go through left borders in non-decreasing order. So we can only remove elements from the multiset now. So while the multiset is not empty and its first element is less than, like the first element is the smallest element, is less than Li, we just erase the smallest element. And here we see that we have the size of the set is equal to the number of elements, the number of segments which satisfy the condition that their index is smaller than the index of the current segment and their right border is at least the left border of the current segment. So this is the number of these segments. And so we have to add actually the number of ways. Okay, so this is binomial coefficient, number of ways to choose k-1 segments from count segments and to the answer. That's what we have to do. And basically, I already have the function which does it. It's not very efficient, but it does the work, does the job. This line is not actually meaningful, but okay. Okay, whatever. This test is done. Good news. Oh, I can now submit. Cool. How did it finish, by the way? And the Gorian 1, solving all the problems in 32 minutes. Great. So we have a lot of unofficial participants, and we also have some official ones. Congrats to the winners. So quite a lot of people solved E. We will take a look at it later. Okay, so I think I'm done with D. Let's check if our solution is correct. Okay, it's obviously it's not correct, but why? Oh, yeah, because again, like I showed my compiler flags, this one is actually quite verbose. But yeah, obviously this has to be strict because comparison of the element with itself should return false. And you have 0. 0 is not correct because we forgot to insert elements into our multiset. We only erase them. So we have to insert the right border of the current segment after we consider it. Okay, 9 is correct. 3 is correct. 0 is correct. 1 is correct. And 7 is correct. Okay. Let's submit our problems now. Okay, let's go actually in the usual order. Okay, A. B. Let's submit both solutions to C1. And C2. Okay, so the two solutions to C1 run in the same very small time, but the second solution took less memory, as expected. And some people said that the segment tree solution to C2 could time out for some people, but I guess this one is very fast. Not even close to timing out. And D is testing. Okay, so we are almost done. We have A, B, C1, C2 correct, and D probably also correct. And we have E remaining. Okay, let's go to E. 80 integers from 0 to 1. Interesting. Okay. We stand in a line, number from 1 to n. Oh, this problem has no useless paragraphs, surprisingly. And lemmings, some lemmings hold shields. Okay. Protection is the number of protected pairs, such pairs that both don't hold a shield, but there's a shield between them. We choose a lemming with a shield. DP value doesn't change. Easy. And total pairs is count of zeros, count 0 minus 1 over 2, and DP. I can put a 0 or I can put a 1. I put a 0 to most have it. Even though this block is not. So I just have 2 blocks in this case, even though this block is not, doesn't have any condition or something. Okay, time limit exceeded. What? Okay, let's mark it as red. How slow is our solution actually? I think it's not too slow. Okay, I guess I can make a test by hand. Okay, 40 zeros and 40 ones, for example. And let's see how slow it is. Is it actually too slow? Yeah, it's super slow. What can I do to optimize it? Yeah, large variable names are the reason, I agree. You're like, yeah. The longer variable names, the slower the solution is. I should have just used 1 character variable names. Because of the for loops within for loops. Yeah, kind of. I mean, I have too many for loops, but can I optimize this solution? We just set the values. Maybe it's actually obvious that you should just pick all the maximums and all the minimums and be ready to go. Some barriers. Oh, so it's actually n to the power of 5. But so it's actually n to 5, but my approach, like my solution was too slow. It's not very nice. Can I throw some light on this problem? Oh, the fastest case 7. Great. $56. Easy, easy. I mean, oh, I knew it. I knew it. So today, hello everyone. How are you all doing? And try to think about what the problem could be. I start right now or after system testing, just because the difference is I can start virtual participation, but since I'm still not like competing, I'm not trying to win. Not that day, but maybe someday in the future. I don't know. It ended like it ended right before Codeforces, right? I'm already baited to wait, but like I'm not sure if that's a good idea. But whatever. Division 1 is the stronger division, and Division 2 is the, I don't know, weaker. I mean, for Division 1 has harder problems, and Division 2 has easier problems. That's all the difference. It was like the ratios are maybe a bit high somewhere, but it's okay. So I guess the difficulty gradient was fine. We'll see. We'll see pretty soon. It's currently 8 p.m. at where I am, which is Belarus. Yeah, you did. You did AD and didn't finish debugging E1. Okay, we'll try to do better. It's okay. It's okay, we'll cut it from the YouTube video and let's just submit first and then we'll discuss. This is obviously the easiest problem, but yeah, hopefully I got it correctly. Will it test quickly? Yeah, I guess. Accepted, yes. Good. So, yeah, problem A, I don't know, like it's a bit, it uses a bit like well-known idea. I think it was used multiple times on my memory. Yeah, I can also turn on the timer, but it's late, so just whatever. Yeah, so the question is about palindromes of lengths greater than 1. And we want the string to have no substrings which are palindromes, right? So what does it mean? First of all, we have some string, I don't know, s0, s1, s2, s and -1. So we want to have no palindromes. No palindromes, I don't know. We want, first of all, no palindromes of length 2, right? So it means that s0 is not equal, should not be equal to s1 if we want the string to have no palindromes. S1 not equal to S2, and so on. And like in general, Si not equal to Si plus 1, because we don't want palindromes of length 2. And then what about palindromes of length 3? We don't want them either. So for example, yeah, this was for length 2, and now for length 3, 1 should not be equal to S3 if we don't want any palindromes of length 3, and so on. And Si should not be equal to Si plus 2, right? So we actually have two conditions which should be satisfied if we want the string to have no palindromes of length greater than 1. And it turns out that these two conditions are actually sufficient. If these two conditions are true for any I, then it means our string has no palindromes. Otherwise, it does have some palindromes, right? Obviously. But any palindrome will have, like if a palindrome is of even length, the two middle characters will be equal, and we will get to this case. And if a palindrome is of odd length, then we will have two characters at distance 1 equal to each other. So we'll have this case. So yeah, what does it mean? In this particular case, we have binary strings of characters 0 and 1. So it means that what we want is actually what I already written here. We have S0 should not be equal to S1, S1 should not be equal to S2, and S0 should not be equal to S2. What does it mean? Like, if we have three characters that should be pairwise not equal, they cannot be just binary 0 and 1, right? So it just means that if length of S is at least 3, then it's always no. Just because in case of binary strings, the first three characters should all be distinct, but they can only be zeros and ones. So if length of S is at least 3, then it's always no. And otherwise, if length is equal to 1, it's obviously yes. And if length is equal to 2, then it's, yeah, just check whether S0 is not equal to S1. If it's not equal, then it's yes, otherwise no. Yes, I will upload this to YouTube. Yeah, I explained quite a lot, but it's okay. Yeah, the code was like this. Just check what I wrote in the iPad. And yeah, so why this is sufficient for any length, once again, like I briefly, like chop x minus problem A. Let's go to problem B. So it took me 1.5 minutes to solve it, and then 6 more minutes to explain it. Yeah, that's fine. Let's go. Problem B. It was decided to build a roof over a football field and consecutive vertical pillars. Okay, some bitwise problem, I see. The heights should be a permutation of integers from 0 to n minus 1. The maximum value of the bitwise XOR of heights of all pairs. Of adjacent pillars. Okay, so we want to find the permutation of integers from 0 to n minus 1, which maximizes this value. Yeah, I feel like, okay, like a bit irrelevant, but I feel like the first paragraph is kind of irrelevant to this problem. Like, I don't generally complain a lot about problem statements. I don't really like this one just because I don't understand, like, this makes zero sense. I think the legends are better when they have at least some point in them. But it's okay, like, it doesn't take too much of your attention, like, you can still figure out what the problem is. I just think it was unnecessary. Going to the problem. Yeah, okay, so we want to minimize the maximum value of XOR. And the question is, can we actually find some lower bound on the answer? Can we find, okay, I guess I should actually type first. Maybe I shouldn't, but it's okay. It's okay, I can just, oh, come on. I can just explain first. So, can you have some lower bound on the answer? So let's say, I know, n is equal to 6. We have some binary numbers from 0 to n minus 1, which are 0, 0, 0, 0, 0, 1. I'll just write them in binary. 1, 0, 0, and 1, 0, 1. Okay? So we want to permute these numbers, and we want to minimize the maximum XOR of adjacent numbers. And so, can you figure out what the answer has to be at least? And it should be at least 4 in this case. At least 1 in this bit. Why is it so? Basically because we have some numbers which have 0 in the highest bit, and then some numbers which have 1 in the highest bit. And we will have to have one of the numbers from the one group and a different number from the other group next to each other. Like, we will have to go from one group to the other group at some point. Like, no matter how we permute the numbers, if we just permute them, I don't know, like this, maybe if we just don't permute them at all, I don't know, like 1, 0, 0, 1, 0, 1. Like, you cannot permute them so that numbers from the same group, from different groups, never are adjacent. So it means that the answer is always at least 1, 0, 0. You cannot make it smaller. And now, how can you actually, like, can we actually make a permutation where the answer is equal to 1, 0, 0? And actually, yes, we can. And for example, in this case, I can see that it's easy. We can just have, like I said, we have two groups of numbers. We can have each group next to each other. We have one group and then the other group. And then all XORs of numbers in the same group, they will all be smaller than 1, 0, 0, right? Because now
numbers in the same group have the same highest bit. And the same, like, numbers in the same group have XOR smaller than 100. And the only place where we can get XOR too big, for example, here, here we'll have XOR at least 100 between the groups, right? When we go from one group to the other. And so we only need to care about this XOR, this black XOR, and how do we minimize it? We just need to have two numbers which differ by exactly that amount, 100. And for example, we can just reverse the first sequence, or we just like we don't need to reverse, like we just need to put 0, 0, 0 and 1, 0, 0 next to each other to get the final permutation. And then here we just write all the other numbers with the highest bit set, and here we write all the other numbers with the highest bit unset in any order. We don't care. Yeah, like first group is highest bit 0 and second group is highest bit 1. So yeah, what can we do? Okay, let's type some code. We have some test cases. We have some n. So like I said, we want to find the highest bit. Let's do it like this. Oh no, by 1, or we can also write like this, it doesn't matter. And then I don't know, let's type p, and then okay, no line break. Okay, like this. Let's see. Okay. I'm pretty sure it should be right, but let's see. Okay, accept. So basically what I did, this. Let's see. Let's go to the next problem. And next problem is problem C. Increase A by 1, increase B by 1, and replace A with the bitwise OR of A and B. The minimum required number of operations to make A and B equal. Okay. Let's see. So what can we tell about the problem? I don't immediately see the solution, but we'll figure it out. So first of all, A is smaller than B. And after we apply any of these operations, we can only make the numbers equal, but we cannot make A greater than B, right? If they are not equal, if A is smaller than B, then after any of these operations, we cannot make A greater than B. So we always have A smaller than B. What else? Oh, no, that's actually not true. Yeah, that was stupid of me, right? A equal to A or B, it could be greater than B. Yeah, of course. Yeah. Yeah, it's actually a bit kind of vice versa, is it? Yeah. Yeah, it's different actually. Yeah, for example, if A is equal to, I don't know, 1 0 1 1 0 and B is equal to 1 1, I don't know, 0 0 here, and we have, let's say, 0 1 1 0, if we do A or B, it becomes equal to, I don't know, 1, 1, 1, 1, 1, 0, right? So it becomes greater than B. Okay, so let's see. Actually, let's solve a different problem. Yeah, as someone mentioned, yeah, A or B is actually at least B, not the other way around. Yeah. Okay. So actually, let's see. What if A is greater than B? What can we actually do? I claim that in this case, answer is just equal to A minus B. Like A greater than B cannot be given to us as the input, but once it becomes so, the answer is actually equal to just A minus B, right? Because we want to make the numbers equal as fast as possible. So we just increase B by 1 to make it reach A. If we apply the first operation, then we only make the numbers farther from each other. And also if we apply the third operation, then it's even worse probably. Okay, the numbers are at most 10 to 6, so 1 million. So we can maybe have some linear solution, but we have... Okay, yeah, I should read this one, right? Yeah, I saw that we actually have 10,000 test cases with 1 million each, but actually we only have the sum of b is at most 1 million, so we can definitely afford the linear solution here and still be fast enough. Okay, that probably makes it easier. So we can probably brute force some number of operations. Like the idea is, like, why did I even talk about a greater than b? The idea is that if we just do a assign a or b, in this case, a becomes at least b. So once we apply the operation of the third type, from this moment, we have a at least b. We always need exactly a minus b operations. That's the idea. So after we make the third operations, we don't have any freedom after that. If we want to be as quick as possible, we should just increase b by 1 until we get to the finish line. So one way, for example, if you want a quadratic solution, I think we probably we can make it linear, but one quadratic solution we can figure out is, okay, let's write it here. So O of, I don't know, b square, I don't know, not maybe b square solution, but anyway, we can just do for x from, okay, yeah, it's actually b square, for x from 0 to, we don't need more than b minus a operations, just because we can always make a and b equal in b minus a operations. So for x from 0 to b minus a, for y from 0 to b minus a, let's say we actually make a equals a plus 1 x times, like assume, and b equals to b plus 1 y times. Like the order doesn't matter here, right? So we can just apply this operation x times and this operation y times. And then let's say that after this, we apply the third type of operation. So we do this after that, and then we apply, yeah, b equals to b plus 1, I don't know, like a nu minus b nu times. Okay. Yeah, actually, I'm already taking probably too much time on this problem, but it's okay. I'm just thinking it through. So how many operations do we need? We need, okay, so we can make answer is equal to the minimum. Let's go. Plus y operations, and plus how many operations? A plus x or b plus y minus b plus y, right? Okay, yeah, that's a bit messy. I don't really like it. Quadratic time. I don't know, actually, yeah, maybe I'm missing something simple. That could be the case. But I think that at least one idea that you can use here is that you actually don't want to try all values of x here. Like, let's say we have some a equal to, I don't know, 1, 0, 1, 1, 0, 1. So that's one case. And then we also like want to increase it. So we can increase it to 1, 0, 1, 1, 1, 0. Then we can increase it to 1, 0, 1, 1, 1, 1. But this case is never better than this case. Like, it doesn't make sense to increase it by 1 after this, because you don't gain anything by that. You only make the answer worse. You increase x in this case, and you also increase this number, right? Always. So we don't actually need to consider this case. We could increase it to 1, 1, 0, 0, 0, 0. And that could be useful. And then again, 1, 1, 0, 0, 1, 0, 1. It's not useful because you just make a new 1 in the number. And then so on. And actually, like, yeah, you can so on. 1, 1, 1, 1, 1, 1 is never useful. And then 1, 0, 0, 0, 0, 0, 0 could be useful, and so on. So I think we can only check some kind of useful numbers of increases to a. Let's try to code it and then see what happens and what the easier approaches are. Okay, like I said, yeah, I should hide my iPad. Yeah, this actually, maybe there's an easier approach. Is there? Should I increment? Okay, so I was talking about incrementing a, right? That's like, yeah, that could be useful. I don't know. It could be useful to increase b, I think. I should also check, maybe, yeah, for example, we can check the example test cases. So in case of 2, 5, you want to increase 5 by 1 and then apply the third operation. But if you don't increase 5 by 1, then you actually get slower. Yeah. So I think you should increase b sometimes. Okay. Let's maybe put my iPad here. So okay. I will initialize like this. And then here I will just actually type the same thing I just did. I just wrote on my iPad x plus y plus 1 plus a plus x or b plus y minus b plus y. And then, yeah, I guess how to go to the next useful number, I should actually just add the lowest bit of a. What is the lowest bit of a? What is the easiest way to find it? New a is equal to new a or new a minus 1 plus 1, I think. And print the answer. One, 3, 2, okay. Let's submit and then we'll see. All right, accepted. So, next. What is the lowest bit of A? What is the easiest way to find it? 1 plus 1, I think. And print the answer. Print the answer. One, 3, 2, okay. Let's submit and then we'll see. All right, accepted. So, is that the solution? Is there any better approach? This is n log n, right? Because when we add the lowest bit, like, yeah, we add the lowest bit. This is kind of the formula from the family tree, yeah, from the binary index tree. How to add the lowest bit to number. This is kind of like, you don't need to know this formula. You can just loop over the bit and then you add it, like, or you can do whatever. Like in this case, it doesn't matter. This formula is just the shortcut. Like you don't really need to know it or understand it to like solve the problem. Okay, there are just 4 ways to change A to B. This can be done in O of n. Just 4 ways to change A to B. Why is that so? I guess we can figure out why some ways are better than other ways. How to do that? Actually, 2 ways only? What 4 ways? Yeah, what 2 ways as well? I kind of wonder. In optimal solution, y is equal to 0 or x is equal to 0, you think? Why is that so? Only increase A or only increase B? That's what many people are suggesting. If we increase both numbers, what happens? I don't know what happens. Like, what happens to A plus X or B plus Y? I'm not 100% sure. Why? Can we brute force all I or B equal to B and get minimum of A or A minus I? I don't quite understand. Yeah, okay. Okay, I'll just explain this formula. Add lowest bit to UA, okay, to X. Let's say X is equal to 1, 0, 1, 1, 0, 1, 1, 0, 0, 0. I want to add the lowest bit to X. If I add the lowest bit, I get to 1, 0, 1, 0, 1, 1. Okay. 0, 1, 0, 0, 0, 0. So like this is the next useful number. Because like I don't want to, like, it makes some other bit different. Like, I don't know how to explain it the best way. And yeah, so the formula is just take x minus 1, which is equal in this case to this. Then you take x or x minus 1, which is equal to this, and then you add 1. But yeah, it doesn't matter. Like again, you can do other, you can use other methods. Whatever. Let's see at the... Can I show the second test? Sure. What is the second test? You mean the second test? Not the second test case, but the second test? I don't know. Okay. Yeah, interesting. I don't know. I guess I will check some proofs later, because you can check all the proofs in Codeforces comments yourself. I guess I'll check them for myself later. I assume there are different approaches you can take, and I don't know, maybe you can can guess your solution. In this case, I didn't actually guess a lot. Like, I think I understand pretty clearly why my solution is correct, but it's n log n. Maybe there is some linear time solution which are more or less tricky to prove. I don't know. Like, yeah. Yeah, I mean, you can come up with a lot of approaches, and then you might get lucky if you don't really understand what you're doing, but you made some formula which works, and then it passes the examples and then passes the whole problem. Good for you. Like, you can also try some brute force solution and then figure out the formula yourself. Like, maybe you can stress test it against some slow solutions, like the quadratic solution I provided, and then maybe some BFS, doesn't matter. And then you can try it this way, and then like you can prove it by stress testing. That's also a way. So you need to get accepted, so it doesn't really matter in general which way you take. But again, in general, you would actually want to understand your solutions, to like have some, maybe not even strict proofs, you don't need them, but at least some intuition why this or that would work. Because I have some solutions in the chat, like I don't understand them clearly, I don't see immediately why they work or don't, but if you can figure out why your solution works, then it's good enough for you. Like, I have my way of solving it, which I understood, but sure, like there are multiple ways, and also like be sure to explore other ways. I will do that after the contest for sure. So seeing how other people approach the same problem is important too. Okay, let's see. I think let's move on to problem D actually. It was enough of problem C. I guess problem C was the most painful problem for most people in this contest. But I showed at least some way to try it. Like always, I will upload this stream recording to YouTube after, in a couple of days, so just check it after that if there's anything unclear, or you can also watch the video on Twitch as well. Even of this stream, you can rewind it right now if you feel like that. Okay, what is problem D? Like this, the idea is that you maintain all okay. subsegment of length at most, well, no, of any length such that the greatest common divisor of the numbers of this subsegment is equal to its length, then the audience will get bored. Okay, that's again like some really cool story. And we can ask any number of times to change a number, and we want to make the smallest number of changes to make the array like good. And we want to know the answer for every prefix. Okay. Yeah, I think this problem is probably easy, but what can we do? Okay, so first of all, I think that we can just find all segments in the initial array that are boring, that have GCD equal to length. We can just find all such segments, right? Can we? Yeah, we just can. Okay, let me code first in this case, and then we'll discuss. Is the stream okay? Can you hear me? Yeah, I think you can. You can hear me. Okay, so okay, I guess there are multiple ways to actually do it. Answer is equal to 0. Yeah. Okay, I'll figure it out. So, okay, let's say I have arrays of 3 of all segments. And now okay, I don't need another array. Okay, from I to I, it's equal to AI. Okay, I guess I can do it in the other order, doesn't matter here. And now I want to merge some segments. Okay, and now okay, and now Okay, it should be this position. If it is inside, then I think something like this. Let's see. Okay, let's submit. Okay. Okay, let's submit. Accepted. Okay. Good enough. So, this problem is, yeah, it has a couple of steps in it. But yeah, my code is probably the easiest you can have in terms of the amount. I guess that you can use some binary search and segment trees and stuff, but you don't have to. I'll check the bot later, yeah. Sorry about that. You use two stacks to make a queue where you can ask for GCD of the whole queue. Then the problem becomes easy. Yeah, there are multiple ways to deal with GCD, but okay, in general, so the idea is that first of all, we want to find all segments which are actually like boring. And we can actually find all of them. And it turns out that there are at most n times log of the greatest number such segments, which I'll explain a bit later. And you can just find them, and then after you find them, it becomes a problem like what? Is it actually like, yeah, I actually didn't think about my solution. Like you can change some number into any into any integer. But my assumption in general was that I have an array, I find all boring segments in this array. They could be like, I don't know, like any type. And then I thought that the problem is kind of like you have to change some elements. You can, I was assuming I just remove some elements so that each segment gets at least one element removed on it. I guess it's okay. You can, is it okay? Okay, let's think. Yeah, okay, I can just change the number to any positive integer. I can change it to any big prime number, which is like not in this array yet. And then all segments of length 1 will have this number, which is not equal to 1. And all segments of length greater than 1 will have GCD equal to 1 because of this prime. And 1 is not equal to the length. So yeah, it works, but I didn't really think about it during solving it. But I think there are even a linear number of bad segments. For every right end, there is only one. Oh, yeah, actually even a linear number. Yeah, I see. Actually even a linear number. But okay, you don't really need this observation. But okay, so when we find all such segments, the question is just how many points. We have a line and we have some segments on the line. And the question is how many points do we need to choose so that each segment contains at least one line. And the solution to this subproblem is kind of like well known, I would say, like it's greedy. The idea is that you sort all segments in increasing order of their right end. So you take the first segment and you check whether this segment contains any points. If it doesn't contain any point, then you take it right bound and you put a point here. Okay, so, and then you don't need to actually check all the previous points, you only need to check the last point, whether your next segment contains the last point you put. So then you take the next segment with the smallest right bound, it contains the given point, so you don't need anything. Then you take the next segment, it contains the given point, like the last point you put, so you don't need anything. And then take the next segment, it doesn't contain the last point, so you put another point at the end of this segment. And the reason about the end of this segment, like not the beginning, not the middle, is that you took the segment which ends in the leftmost possible point. So any other segment ends to the right of this point. So if you move the point you choose to the left, you don't achieve anything. You don't allow any new segments. That's the idea. So you can always put it to the right point. So that's kind of the greedy idea in general for the problem about segments on a number line. And then how do we find all such segments? Let's go from left to right. Okay, for example, maybe we can check the exam, like the actual problem example. Can we? Yeah, let's just try this array of numbers. So we have 2, 12, 4, 8, 18, 3, and 6. So you go from left to right, and for each prefix of the array, you want to find all different GCDs, all different greatest common divisors on the suffixes of this array. So for example, you take 2, and here you can only have GCD equal to 2, right? You take 12, and here you have two options. If you have a segment of length 1, its GCD is equal to 12. If you take a segment of length 2, its GCD is equal to 2. So then you take 4. What do you have? You can have length 1, GCD will be equal to 4. You can have length 2, and GCD will be equal to 4 as well. And you can then take length 3, and then you have GCD equal to 2. So the idea is that you, okay, let me just do it like this. The idea is that you maintain all segments where, like all segments of left positions where GCD is equal for a fixed right position. So for example, in this case, when we are at 4, we have one segment from position Z. Okay, so positions are numbered 0, 1, 2, 3, 4, 5, 6. So from position 0, like let's say the right bound, I equal to 2. So first, from position 0 to position 0, if the left bound is from 0 to 0, then GCD is equal to 2. So like from 0 to 2, because we just have GCD equal to 2. And then if the left bound is from 1 to 2, then GCD is equal to not 2, but 4 in this case. So you maintain such tuples of 3 elements. You can probably have pairs, but it doesn't matter. And you just, like, each tuple is from, to, and value. And it means that for any subsegment such that left is from to right, from to 2, and right bound is equal to I, GCD is equal to V. So you just maintain all such tuples. And then when you go to I plus 1, it's actually easy to change these tuples, because you just, so what happens, you take all the tuples, in each tuple you change the value to GCD of that value and this value, and you put a new tuple, which is for the one element segment, you just put a tuple for a segment of length 1, yeah. And then you can also merge segments which correspond to the same value. You take pairs of neighboring elements which have the same value, you can just merge them. So I just like merge them here. And I remove, like, decrease number of tuples this way. And then the main idea is, why is it fast enough? Like, why is it better than just checking all possible subsegments, which you have n square of them, right? But why is it better? It's better because GCD is actually decreasing quickly enough. So in general, like, yeah, you can probably find this idea and this technique in multiple sources. I don't know, multiple problems probably, right? I don't know about sources because, like, it's not some standard algorithm, but it's kind of an idea which appears from time to time in problems. Let's say you have some GCD here, okay, G0, you have some GCD here, G1, you have some GCD here, G2, and so on. You have some GCD here, G and minus 1, I don't know. So you have GCDs of all suffixes of some array, let's say. So first, what do you know? You know that G0 is greater than or equal to G1, right? Because when you include a new element, the greatest common divisor can only decrease. Greater than or equal to G2, and so on. Greater than or equal to Gn minus 1. And then another thing that turns out is that Gi is always equal to Gi plus 1, or Gi is at least twice Gi plus 1. So just because obviously Gi is actually divisible by Gi plus 1, right? So since we know that, just because it's like some divisor of, we ended a new number, so GCD can only be a divisor of the old GCD. So since we know this happens, it's like the result of division is either just 1, in which case the numbers are equal, or it's 2 or more, so in which case we have this case. And so what follows from this is that the number of distinct values among G0, G1, Gn minus 1 is at most log of G, okay, O of log of G0. So it's actually binary logarithm, but it doesn't matter. Because every new number should be at least twice smaller than the previous number, right? So yeah, GCD changes at most not log n times, but log biggest number times, right?